So now we're going to be taking a look at some examples of being able to write geometric sequences in both recursive and closed forms. Now remember, geometric means that there's a common factor that separates each of the different terms. And one of the things you might want to do is determine whether the sequence is going to be geometric or arithmetic. Now notice it's not arithmetic because the first two terms, d would be equal to 10, but then the next d would be equal to 30. So that doesn't make any sense. You have to have a common difference if it were to be arithmetic. All right, so clearly this is not going to be an arithmetic sequence. However, we're hoping that we can get a common radius. And in this case, r, well, to go from 5 to 15, you would multiply by 3. And then to go from 15 to 45, you would multiply by 3. So it looks like that in this example, it is indeed geometric, and r is going to be equal to 3 for us. All right. So let's first of all look at the recursive formula. The recursive formula says that we just have a sub n is equal to r times the previous term. Okay, so for letter A, if we're to build a recursive relationship, a sub n is going to be equal to 3 times a sub n minus 1. All right. Now, we want to start this with n being greater than or equal to 1. And the reason that is because if you look at a sub n minus 1, well, you can't plug in a 0 because that would give you a sub negative 1, and that doesn't make any sense. We have to define the initial value. In this case, the initial value, a naught, is going to be 5. All right? So this is how we would write a recursive relationship. All right? We know that's very expensive with respect to memory. So now let's try to build a closed form. All right? In this case, a1 is the first term is 5. And so we can build our closed form to be 5 times 3 to the n minus 1. All right, and that would be the closed form. We're going to say that n is greater than or equal to 1, and if we wanted to be really specific, we could say that n has to be an integer value. All right, so there's going to be our closed form. And then the last thing that we're asked to do is to be able to find the 10th term in the sequence. Well, we could just go ahead and find a10 readily. 5 times 3 raised to the 10 minus 1th power, or 10 minus 1 power, excuse me. And I'm going to compute that really quickly. It's probably not going to be a nice number. It's not too terrible. So it's 98,415. Right? Certainly much quicker than us going through and doing the recursive method. All right. One final example. Right. This one's not as easy to determine r, but it's not too awful. Right. So we have 4 8/3, 16 9ths, 32 27ths. And one of the ways we can be able to figure out what r is we could just clearly look at two of the fractions. All right. And we do know that this one's going to be recursive. It's going to be geometric because we notice that each of the numerators is being multiplied by 2, and each of the denominators is being multiplied by 3 to get to the next denominator. Think of 4 as 4 over 1, if that helps. So we know that r is going to be equal to 2/3 in this example. And if we're going through and we're doing the recursive method of this, we're going to say that a sub n is going to be equal to the initial value. So we're going to go back up here, and we know that we have r times a sub n minus 1. So r is 2/3 times a sub n minus 1. We need an initial value, so we know that a naught is going to be equal to 4. And we should probably say that n is going to be greater than or equal to 1, so that we have a domain for this. If we want to try to put it into a closed form, a sub n, and we go back up and we look at our formula. Our formula for our closed form is the initial value, which in this case was 4, times r to the n minus 1 power. So that's going to be 4 divided by 2/3 to the n minus 1 power, right? Which is going to be with the condition that n has to be greater than or equal to 1, right? Otherwise this doesn't work. So we get rid of this equals. So we're going to say n greater than or equal to 1. If we really wanted to, n could be an element of the integers. All right. Just as a heads up that we could simplify this a little bit, okay? And let me illustrate how we can simplify it. We could simplify this because we know that 4 is 2 squared. And we could go through and we could distribute that n minus 1 power. And we're going to have to use this in the next section anyway, so that's why I'm trying to illustrate the algebra of this. Right? And notice that we have a common base of 2, so we can multiply those together by adding the exponents. So another way to write this would be 2 to the n plus 1 divided by 3 to the n minus 1. All right? So that's another way to be able to write this sequence in closed form. It's a little bit cleaner actually, so we can do letter C fairly easily. We're finding A10, so that's going to be 2 to the 10 plus 1 divided by 3 to the 10 minus 1. All right, and I'm going to throw that into my calculator. So 2 to the 11th is going to be 2048. And then 3 to the 9th power is going to be 19,683. All right. So that's going to be our closed form, as well as our recursive form, and then being able to find the 10th term in the sequence. All right, so hopefully this is helpful for you guys to be able to take and see the relationship of recurrence relations between two sequences that can be written in closed forms. In the final set of videos for this section, what we're going to be doing is we're going to be taking recurrence relations and we're going to be turning them into closed forms to make them much easier to deal with.